Okay, now that you're pretty good at all the different types of energy, kinetic, gravitational potential, and elastic potential, it's time to look at something that's called the conservation of energy. Because really, energy in the universe is neither created nor destroyed. It just really changes form. The way we saw in that efficiency question with the kid on the slide. The kid starts at the top of the slide and has gravitational potential energy. And when the kid gets to the bottom of the slide, that gravitational potential energy has turned into kinetic. And maybe some has turned into heat as a result of the butt sliding down the slide and some heat being generated. Now, before we talk about conservation of energy, I need to talk about two different types of forces. There are what are called conservative forces and brilliantly labeled non-conservative forces. And I think you'll understand the difference between these. If you think about, imagine so here's a table, and I raise a book above the table. So I do work, and I'm holding the book up here, right? So I've done work to move the book up. When I let that book go, I've done work to move the book up, and the book now has some gravitational potential energy as a result of the work I've done. When I let that book go, release it, now gravity does work on the book, and it changes the gravitational potential energy into kinetic energy. And assuming there's not a major wind current or anything, the amount of gravitational potential energy it gained from me doing work against gravity will be equal to the amount of kinetic energy that it picks up as gravity does work on it. Okay? And when I lift this book up, I could have lifted it straight up the way I have my arrow here, or I could have lifted it up through some kind of weird circuitous route. But as long as I got to the same spot, its gravitational potential energy would be the same. The work done against gravity, it doesn't matter the path you take. All that matters in the end is the change in height. Gravity is a conservative force. A conservative force, then, is a force that does work on an object in such a way that the work done is independent of the path and is reversible. Okay, so gravity is a conservative force because I do work against it, and then when I release it, I get the same amount of energy back out. So conservative forces are independent of path and reversible in the sense that I can get the energy that I've put in back out. And an example would be gravity. Now, imagine my table again, and this time, imagine me pushing a book across the table. So as I push my book across the table, I'm changing the kinetic energy of the object, right? It'll pick up speed. But when I stop and release it, it doesn't move back, right? It's not reversible. When I'm pushing it across the table, I'm doing work against friction. And the work that I've done against friction, I don't get back. Friction is a non-conservative force. It depends on the path, right? If I move it straight across the table, or if I do zigzags, I'm going to have to do a lot of more work in the zigzags because I'm going to encounter a lot more friction along a longer path. So it's dependent on path, and it is irreversible. That energy I can't get back. And an example would be friction. So whenever I'm doing work against a non-conservative force, we often say that energy is lost. It might be lost because it's turned into a form of energy I can't use, like heat or something like that. Okay, so that becomes important when we get to now our conservation of energy. Okay, and so what the conservation of energy says is very similar to what the conservation of momentum said. It says the total initial energy total energy initially should be equal to the total energy finally. Whether I'm sliding something down a hill, whatever I'm doing, if energy is conserved, then the total initial should be equal to the total final. So if we look at mechanical energy, remember those are the three kinds we've been looking at, that would say the initial kinetic energy of the object plus its initial gravitational potential plus its initial elastic should be equal to its final kinetic plus its final gravitational potential plus its final elastic. And in a perfect ideal world, this would be true. However, in our perfect world, our world is not always perfect, and usually there is some energy lost. So we usually, instead of talking about conservation of mechanical energy, we use conservation of total energy. And it looks exactly like what I just wrote down. So it's the kinetic energy of the object initially, plus its gravitational potential initially, plus its elastic potential initially, has to be equal to its kinetic energy after the event, plus its gravitational potential after the event, plus its elastic potential after the event, plus anything that has been lost. We call it E lost. Now this E lost is really work done by friction. And we know work done is equal to F delta D cos theta. So really, if we ever are solving for E lost and get it, I could ask you to find something more because this F is friction. So E lost then is equal to FFR delta D cos theta, where of course FFR is equal to mu Fn. Okay, so it will take a day or two before we'll get to E lost, but just when it does, it's just work done by friction, and we'll use that to find it. All right, so let's try an example, and we'll start with an easy one. So let's say we're at the top of a hill, top of a building, and we're going to drop an object, and there's no air resistance. So example one. So it's a 20 kilogram object up here, and it's at the top of a building that is 100 meters high. This is a real building. And we want to know what's its speed just before it strikes the ground. Now, don't tell me it's 0. It's going to be 0 after it hits the ground, but not before. If it was before, everybody'd be wanting to be dropped off the top of a building. So you start out by writing your big long equation down. 1/2 mv initial squared plus mgh initial plus 1/2 kx initial squared is equal to 1/2 mv final squared mgh final 1/2 kx final squared plus E lost. Now this might seem huge, but it's really just the little components put together. When I read the question there a minute ago, I said assuming no air resistance, so E lost is gone. And so it might look awful, but you say, okay, at the top of the building, before I drop this object, I'm just holding it here. So there's no speed, so this term goes. Is there a height? Yeah, so mgh stays. Is there a spring? No, this term goes. When it gets to the bottom, there's a speed. That's what I'm looking for. Is there a height? No, it's just before it hits the ground. There's no spring. So this big long equation collapses to just this. M's are the same. They cancel. I'm looking for VF. Multiply both sides by 2. So it's 2 times 9.81 meters per second squared times 100 meters. And then don't forget to take the square root. And when you do, you get 44.294 meters per second. So it might look